Good afternoon, dear colleagues, ladies and gentlemen. Me is Igor Pegel from the Institute of High Current Electronics, Tomsk. So I'm the chair of this session. I'm pleased to open the oral session for numerical simulation in high current electronics. But before we start, let me remind you our rules. The speakers have 30 minutes for an invited talk, and which includes 25 minutes for the talk and 5 minutes for the questions. Then the oral talk is 20 minutes, which means 15 minutes for the talk and 5 minutes for the questions. All the questions should be asked after the talk in the comment chat. I will voice any questions to the lecturer. Then, for the successful session, you need to have a stable internet connection. You need not to forget to switch on your web camera, your phone, and when you start your talk, you should not forget to click the button "Go on Air." So all presentations are broadcasted from the webinar cloud. So some sessions go in parallel. So if there will be some overload of the system, so it may result in some delay in the system response. Okay. I'm pleased to give the floor to our first lecturer, which has an invited talk. This is Professor Lijun Wang from the Xi'an Jiatong University, China, which will give the talk Modeling of Vacuum Arc in Anode Spot or Anode Plum Modes with consideration of different compounds. Please, Professor Lijun Wang.
Thanks, Mr. Chairman. Can you see my voice? Can you see my screen?
Yes.
My screen?
Yes. So we see your screen?
Yeah. My PowerPoint?
Yes. It is on the screen.
Yeah. You can see. So, okay. Good morning, everyone. I'm Lijun Wang from Xi'an Jiatong University, and I'm very honored to have the topic about the modeling of vacuum arc in anode spot or anode plume modes with consideration of different components. And we have cooperation with Dr. Shmelov from Russia. My topic includes 5 parts. The first part is introductions, and the second part is model descriptions, and the third part is the simulation results, and the fourth part is discussions, and the final part I will give the conclusions. So the first is introduction. As we know, in the vacuum interrupters, when the arc current is small, the cathode spot is the most plasma source in the interelectrode. But if the arc current is big enough or large enough, the anode will become another plasma source, and the anode will be melted and evaporate. Then the anode vapor maybe will possibly enter into the arc column. And most experiments used the electrodes with smaller diameter, maybe a lot 10 millimeters to study the anode phenomena, because in this case the anode plume or anode spots phenomena will be more likely to be observed in this case. And this figure shows experimental result about the anode spot or anode plume phenomena. It is conducted by Dr. Bartkov in 2010. And the main component of the central dark in this rejoin area is neutral atoms, while the error outside the lighter layer is dominated by the ions. And in the layer, here is the layer, the ionization and the recombination process is very intense. And in our former work, we have studied the anode phenomena with a smaller electrode. The electrode diameter is about 10 millimeter. However, this kind of phenomena can also be observed in the experiments with larger electrodes. This work is for the experimental result for the larger electrode. This is conducted by the Dr. Kuhn, and also this image is conducted by Japanese colleagues for the vacuum arc image, and also very strong anode vapor and anode melting phenomena can be observed. Moreover, AMF also can influence the anode phenomena. And in this work, in order to understand this kind of phenomena, in this work, a three-dimensional MHD model is established to simulate the anode spot mode, considering realistic AMF generated by cup-shaped electrodes, because the cup-shaped electrode is very popular commercial AMF electrodes.
Oh, excuse me. Could you please change the slides? Change the slides.
Change the slides?
Yes.
Okay. Yeah. Can you see?
So unfortunately, we still have one and the same slide. Or
okay.
In this case, please tell if we have to show the next slide. And I will.
Okay, maybe this pointer. I'm not sure.
You have the right arrow in the lower part of the screen.
Can you see this? Sorry. Oh. Okay. Can you see the next?
Yeah, yes.
Screen? Okay. Sorry. Yeah. Can I continue?
Yes, sure.
Yeah. Next, the second part is model description. And this is the model, the physical model. And here is anode. Here is the cathode. The arc current is flow from anode to the cathode through the vacuum arc area. And here is the cathode spot, and here is the cathode spot and the mixing region. And here is anode sheath. And for this region is the calculation region, calculation area. And in this work, we use the our current is 25 kiloampere, and the contact diameter is 58 millimeter, and the gap distance is 10 millimeter. For the contact material, we use a copper chromium 25, and the maximum anode temperature is from 2,200 to the 2,400 Kelvin. And from this model, we can see if the anode temperature and the anode vapor are high enough, a lot of neutral atoms will enter into the arc column. Here is the arc column, and from a low ionization degree area called the neutral atom vapor area, we call a navel. In front of the navel, the ionization is very intense. It is called ionization layer. This is ionization layer, and outside the layer, the arc column area with high ionization degree. This arc column with a very high ionization degree, and in our model, we consider the ionization and recombination process. Friction force among different species and the energy exchange among different components, and also we consider the influence of anode sheaths. And this is a mathematical model about the control equations. First is this is mass conservation equations, and this equation is related to the single charged particle mass conservation. It includes copper and chromium, single charged, double charged, and triple charged particle. And this is atom mass conservation equations. And here alpha is the ionization coefficient, beta is recombination coefficient, and here AGI means dot means this means net ionization rate, and this formulas is the relationship among the different species. This is the electron number density. This is the copper and chromium number density, and we can get the mean charge number. We can get the mean charge number by electron number density over ion number density. And this is momentum conservation equations, and this one is ion momentum conservation. It includes copper ions and chromium ions, and this equations is atom momentum conservation equations. It also includes the copper atom and chromium atom. And this is energy conservation equations. And the first one is for the ions energy conservation, and the second one is for the neutral atoms energy conservation, and this is for the electron temperature. And we also consider the other consequences is this is mass magnetic field transport equations, and these equations from these equations we can get the magnetic field distribution, also can get the current density, and these equations is derived from the general Ohm's law and Maxwell equations, and this equation is general Ohm's law. And for the above equations, we use several samples, and the different samples have different meanings. Here, NS means total number density of species, and the US is the average velocity of species, and the PS means the total pressure of species, and the mass means the particle mass, and AG means the net ionization rate, and the G and the B means the current density and the magnetic field. Here, RIA means the friction coefficient between the ions and the atoms, and the TS means the average temperature of species. And here, phi means the potential, E means the electric field, delta means the electrical conductivity, and so on. So the subscript S means the species. When the I means airs, and the E means electrons, A means atoms, and the subscript A means the materials. We use the copper and chromium material. And the subscript G is ionization state. When G is equal to 0, it means the atoms. And when G is larger than 0, it means the charged ions. So for the boundary conditions, the ions are generated from the cathode side, while the atoms comes from both cathode side and anode side. For the anode side, the anode vapor is very strong. The boundary conditions for the ions are similar to our former works, and the influence of anode sheath is considered in the model. And this is the boundary conditions for the neutral atoms. We use these formulas. Here, TAM means the anode surface temperature distribution. TAMP means the maximum anode temperature. It is from 2,200 to 2,400 Kelvin. And here, R0 means the attenuation coefficient of anode temperature. And here, P site means the saturation vapor pressure. And here, gamma means adiabatic index. M is a Mach number. So the third part is simulation result. First, we give the actual magnetic field distribution. First, we get this AMF distribution from ANSYS software. We use this kind of couple-shaped electrode, and current goes through from this direction, and from this electrode cable and the cup and the core, we can get the actual magnetic field, and then we can put this AMF distribution to the vacuum arc model, get the other plasma parameters. And here is the AMF distribution along the YOZ plane, and this is AMF distribution along the cathode plane and the anode plane. From this figure, we can see the AMF is stronger at the center region of electrode, and it is lower or small at the edge of the electrode. And the maximum AMF is about 150 millitesla at the slots. So this is typical results. We give the TAMP is 2,300 Kelvin, and this is the distribution of air density along YOZ plane and the anode plane. and this is the actual current density, and this is the electro temperature and electro temperature along YOZ and the anode's plane. Since the anode, since the anode vapor is generated at the anode center, the atoms are ionized in the navel, leading the high air density here. The air density is very high. The current density is high near the slot. Since the current direction is changed rapidly at the slots, and at the cathode center, the current density is low, which is due to the low electrical current density in the current conductivity in the navel, and the temperature inside the navel it is low due to the energy consumption and caused by ionization and energy exchange. And this is distribution of different components. Here, the left side is the copper atom density. The right side is the chromium atom density. And this is a copper, single-charged copper. This is a single-charged chromium. This is double-charged copper, double-charged chromium, triple-charged copper, triple-charged chromium. And from this figure, we can see the atoms and ions are ionized to the higher ionization level, step by step, from 0 to 1 to 2 to 3, compared with copper particle. Chromium particle are more likely to be ionized to higher ionization level due to it has lower ionization energy. And the highest atoms can be seen at the anode center. Inside the navel, atom density is much higher than air density. And the triple charged air density is very low and reaches its maximum value, where the electrode temperature is high. We also have studied the influence of the anode surface temperature. We change the temperature from 2200 to 2400. And for the figure A is the TAMP is 2200 Kelvin. B is 2300. C is 2400. And for D fig, we don't consider the anode vapor, the influence of anode vapor. This is air density. This is atom density. When the anode vapor is not considered, we can see these figures. Atom density is only about 10 to 19 per cubic meter, and can only be seen near the cathode side. But considering the anode vapor, the maximum atom density is more than 10 to 23 per cubic meter. And with the increase of the TAMP, the atom density and the navel increase gradually. However, the increase is not very significant. And this is electrode temperature distribution. We consider different anode surface temperature. Anode vapor can only influence the electrode temperature at the anode center, because where the anode vapor and the density and the number density is very high. And with the increase of TAMP from 200, 300, 400, electrode temperature at the center decrease significantly, slightly. That is to say, the electrical temperature is in inverse proportional to atom density. And this figure is the anode sheath potential drop along the radial direction of anode, varied with the maximum anode surface temperature. We have different anode surface temperature, and this is a formula for the. This is a formula to calculation the anode sheath. From this figure, we also can see the potential. The potential drop mainly depends on the electrode temperature, and near the anode edge, if y is equal to 25 millimeter, the potential drop is highest because the electrode temperature is the highest near the slots. And when the y is larger than 15 millimeter, this region, all these curves have the same distribution, indicating that the anode vapor can hardly affect the plasma parameters at this region. And at the anode center is another. At the anode center, the potential drop is only about -2 volt. And with the increase of TAMP, the anode sheath potential drop is lower, but its decrease is not very obvious. And the fourth part is discussions. This is the simulation result of our former work. The small electrodes is used to simulate the anode phenomena. In this case, the current is about 4 kiloampere, and the electrode diameter is about 10 millimeter, and the gap distance is 5 millimeter. And this work have published the Journal of Applied Physics last year, and most conclusions are similar to those in this work. And this is a comparison with experiment. And this experiment has been conducted by IMP. We can see the simulation result is in agreement with the experiment result. And these two figures is this above figure is simulation result in this work. And this figure is simulation result from our former work, smaller electrode. And these two groups of results show the similar trends. And this black line is air temperature, and the red curve is the electrode temperature, and the blue one is the atom density. And these two groups results show the similar trend with the increase of TAMP from 2,200 to 2,400. The atom density is higher, becomes higher, leading to the lower plasma density. However, the anode area with high temperature is larger in this work, which leads to more anode vapor and a larger number. Thus, the plasma temperature is lower than that in our previous work. When the TAMP is higher, anode density does not increase significantly as in our previous work. This is because of a more rapid ionization of atoms, which is due to the first is a high current and then higher energy, and a larger interaction area, ionization layer between the naval and the column with the larger electrodes. So the final part is conclusions. In this work, a three-dimensional model is built to simulate the influence of anode vapor on the vacuum arc, considering the realistic AMF. And anode vapor can form a cool naval dominated by the atoms. Outside the naval, atoms and ions are ionized to higher ionization level step by step. However, the triple charged ion density is very low. The plasma temperature, especially in naval, is lower than that in our previous work, a smaller diameter due to more anode vapor. In the current working condition with larger electrodes and high current, it is hard. It is very hard for anode vapor to enter into the arc column due to the high energy and larger ionization layer. Thank you for your attention. Thanks. Do you have any questions?
Excuse me. Thank you very much, Professor Lee Jun-Wan, for your impressive talk. And we are going to questions. And the first question was by Elena Korukina. Which computer program did you use for solving your differential equations? Was it your own code or something else like console code? Your plots look like console plots.
Yeah, we use Fluent software, but for the current and magnetic field calculation, we need write the code, work with Fluent software.
Thank you. No more questions. I have a question. What's your estimation? How far or how close are you now to completely describe all the key physical processes which occur in the gap of a vacuum discharge?
Estimate?
What is your opinion? How far are you now in your simulation to completely model all the physical, all the key physical process in the gap of the vacuum discharge?
Yeah. Yes. In this work, I think we can compare it with simulation, the experimental result. Just only for the vacuum arc image, and maybe further we need complete the model. Compare the simulation result with the plasma parameter. Also, because in this case the measurement for the parameter is a little difficult. But at present, there are some experimental results. We can compare with that and improve our model. At present, the model is good. It can predict some plasma parameters and images.
Thank you. And I have one more small question. What is a typical simulation time? And what is a computer performance in petaflops or teraflops? How much time takes a typical run takes?
Yeah, for the three-dimensional model, we need about 2 days. 2 days, and at present, my students always use workstations. Maybe we use 8 cores.
I see.
8 cores workstation.
Thank you very much for your lecture. And now we are going to have. Thank you. We are going to talk, which will be given by Dr. Mikhail Tventukh from Lebedev Physics Institute of Russian Academy of Sciences, Moscow. The title of the talk is Explosive Electron Emission Pulses Plasma Parameters Estimation from Model Based on Transition over the Critical State. Please, Mikhail.
Hello to everybody. Good morning, Mr. Chairman. It's okay, can you hear me?
Yes.
Okay. It's great, thank you very much for the opportunity to make a presentation of our recent results. And my talk will be on another side of the work that just has been presented by Professor Lujin Wang. So I will speak about the cathode processes in vacuum arc. What we can estimate from not so difficult, not so complicated model, but not phenomenological model, but a little bit more complicated, but simple model. What we can derive in plasma parameters of interest for estimation of parameters of vacuum discharge. So I will change slide. So recently we have many models that explain how plasma being produced during the vacuum discharge. Basically provided by explosive electron emission events at the cathode with dense plasma splashes from the cathode that produce electron emission and also plasma filling of the vacuum gap. And it is known that they are of very large electron density, in particular near the cutoff of optical wavelength, so about 10 in 20 in 10 in 21 cubic centimeter, and fast term processes with nanosecond time scale and microns in special size. So it's difficult to model in general manner, as you already asked, how we far from the complete modeling or estimation of complete parameters. And furthermore, they interact with each other, so it's resemble a process of boiling at the surface. The larger the bubbles of boiling liquid, larger the material can be extracted from the surface. So they interact with each other. This explosive events, explosive pulses. And recently, we have proposed a simple model, which, in addition to the previous models with image D or kinetics, with detailed numerical simulation of processes, we have proposed simple model to estimate some basic parameters for broad range of materials. To how we can estimate some simple parameters from simple model. This model was as follows. We have I would use this. They have liquid metal jets that arises from a previous explosion under the large pressure of plasma, and these jets are believed to responsible for self-sustaining of the burning of such explosive events. And if we use the model of liquid metal tearing of a jet, we can estimate some parameters. So the model is assumes that during the tearing of a liquid metal jet, it goes through the critical state. Critical state is such a state of matter with temperature about 1 eV and almost solid state density, and it characterizes by vanishing of cohesive energy. So at normal state, the cohesive energy is about few electron volts, and in the critical state there is no cohesive energy, so ions can leave the surface without losing of energy. So it's favorable for production of for intense production of plasma. And furthermore, there is reducing of ionization potential due to non-ideality of plasma. So also reduction of ionization potential is helpful for production of plasma. And there is tearing of jet, increasing of current density, transition of critical state, and we can propose some simple model. There is some example for various of temporal evolution for some simple critical temperature for various materials. And we catch three main parts: ignition, explosion, and expansion of plasma after the explosion. So they have three main parts of the problem. We can describe it. What we can derive from this model? We can derive the mass of ions related over the current density of the value number of electrons. So how much plasma should be produced for the current that we want to transfer. And this is characterized by this ratio of average pressure of the pulse to the average current density. So we have strong variation in pressure and in current density, and we can estimate the average values over this pulse. And this value is can be estimated to be about tenths of grams centimeter per second coulomb, and this value is close to product of velocity of ions that can be measured, and erosion of specific erosion of ions, and also it corresponds to velocity of droplets that can be also measured, and maximal erosion rate for liquid metal droplets also can be measured and can be seen. So the momentum, this momentum per transfer charge, responsible for the erosion processes. And the important point that we can estimate the electron drift velocity. it's important to identify some estimation of this value. It can be measured during the explosion because the small scale and this electron velocity is problem. And the question is that it can be close to ion acoustic velocity like we obtained here, or electron velocity. There is 2 orders of magnitude difference between them. And our estimation shows that this velocity is enough to current transfer and enough to provide necessary momentum of explosive plasma necessary to providing the erosion and acceleration of plasma. It is enough to they have we can use this estimation, and it depends on mass and on critical temperature and average charge, of course. Also, we can estimate from this model other specific things like average ohmic electric field. So we have current transfer through the media, and we have some ohmic electric field that arises due to this that provides this current transfer. And this estimation is shown here. It shows that about tenths of kilowatts per centimeter. It is some electric field that can be provides the current transfer. And all the cathode pole that is about tenths, maybe 20 volts, can be provided within this explosive plasma in few microns. So this electric field can provide with plasma. This electric field can provide all the cathode pole within few micrometers. It corresponds to observation of small-scale plasma, and it corresponds to known cathode pole. In fact, also we can estimate total current. So we can use some geometrical consideration. If they have explosion of the neck with a small radius, so how we have longitudinal size of few microns. So from simple geometry we can estimate it to be about 1 ampere. That corresponds to observation of threshold current in vacuum arc. So if they use this model with the explosion of liquid metal jets, we can estimate threshold current. And there is some certain estimations for the conductivity of the media and for cathode pole, just for example. It's surprising that similar column-like geometry has been recently observed in hydrodynamic simulation and measurements. So there is on the right side with the photos of liquid metal, not metal, just liquid jet chain, and modeling from the bottom, at the bottom. And similar column structure is observed due to this during these investigations. Other important thing of using such estimation is effect of magnetic field on ensemble of cathode spots, on ensemble of the cathode spot cells, and they have estimated this influence in ImageD approach with weakly magnetized plasma, and we have shown that there is some contraction of dense plasma not pinching like in typical pinch devices, but a little bit slowing down on the reticular side, on the side with the larger total B field, and this simply results in this slowing down results in increasing of density. And but originally this approach need to specify the current drift current electron density, electron velocity, and if we use this velocity that can be derived from this critical state model, we can estimate it more correctly. Other results with this model is results from recent studies on arc burning at some specific surface, tungsten nanofast structure. There is a grade of network structure at the surface with nanometer size wires, and arc burns on these layers of these wires, and it was shown that charge states can be vary with the thickness of the structure, with burning on the top of this layer or bottom. So I will show a little bit further experimental results. First frame is demonstrates measured ion spectra when burning of arc is rises at the top of the layer. Middle is burning of arc at the middle, and final frame is burning of the arc at the bottom of the structure. So there is no structure. Almost normal tungsten remains at the surface. So this situation is normal burning of arc at the tungsten surface. And here we have many nanowires with weakly bonded at the surface. So if we propose that the effective critical temperature will be lower for this structure, that essentially that should be, in fact, we may see the correlation between lower critical temperature and lower average charge of ions. And I'm sorry, and we can estimate average charge by relatively simple Sakha-like equation for the average charge, and we can obtain some estimation that average charge is about temperature of the AD, and the linear dependence between average charge and temperature, and it's simple estimation, but it nearly corresponds to our observation if we propose that dependence of critical temperature and arc properties is essential. Other things is also from this recent experimental results on a composite and intermetallic cathodes. There is some mixture of materials, and there is arc burning voltage for these materials, and spectra of ions emitted from cathode spot. And one can see here that for pure materials, there is for niobium and alumina, there is normal high enough energy ions are present in the spectra. But if we use a mixture of materials with fine structure of the surface, energy is much lower. So it's possibly it can be also related to the effective critical temperature. if they have some microstructure or nanostructure at the surface with weak bound of grains, we can get lower energy of plasma production, in fact. And this can be explained from this point of view. In particular, we have a relation with the ion acoustic velocity and observed ion velocity rate after acceleration from the cathode spot at a far distance from the cathode spot, and there is a good correlation between them. So we can see that for different materials, this relation acceleration properties starts from transitional critical state, and here we can see that lower velocity and lower kinetic energy of ions, in fact, can be attributed to the lower critical state. So this finally, I would say, some concluding remarks. So we have proposed a simple model for estimation of basic parameters of plasma, and our recent point is that if you'll take into account fine structure of the surface, we can explain properties of arc cathode spot plasma with closed processes burning out at fine structure surface. So another effective temperature, with another effective critical temperature, with effective critical state, we can explain properties of arc burning at fine structure surface. Thank you very much.
Thank you, Dr. Pentuch, for your very interesting talk. And we are going to questions. I do not see any questions for a while.
That's great.
May I ask a question?
Sure.
In your opinion, how wide or how narrow is the set of possible experimental situations where your scenario of forming a drop which flies apart, forms a jet, and this jet tears, and this gives a plasma through by going through a critical condition? How wide is set of experimental situations where this mechanism plays is a key mechanism? Do you believe this mechanism is a key mechanism for the explosive emission at all?
There's difference between, let's say, high voltage discharge with the vacuum breakdown or vacuum spark with high voltage, and low voltage arc discharge. So there may be difference between this kind of discharge, in fact. So we have shown previously that for large enough energy flux to the surface, we can drive explosive processes without any at a flat surface. So then, formally, we do not need any non-homogeneity on the surface. But here, it was interesting to analyze some threshold low energy flux conditions. So it's related to the vacuum arc, first of all, and for basically for clean metals. So clean metals with splashing of material, we see that it's known that the splashing of materials at a clean surface. If we have contaminated surface with some films and so on, we can get some lower thresholds or some another process with charging and so on. But it is difficult to analyze some contamination at the surface, because what means contamination? It can be of different nature, in fact. And our extension of this work, in fact, for some fast surface with nanowires or nanograins in the surface, helps us to extend our model to some real surface with some inclusion on some real surfaces, I would say, because this we believe that it can be done by effective critical state. So there is no maybe not strictly extension of liquid jets and TN, because in fact for the tungsten nanowires we have no liquid metal at the surface almost until it burns to the bottom. So a few microns of this layer provides effective burning of arc without liquid metals. But probably we can use some extension of this model of critical state for with effective average state for some real materials. It means that we can derive some more general model.
I see. Thank you for the very detailed explanation. Alexander Pushkarov is asking, what is about the explosive plasma density?
It changes in time from solid state, from critical state. So it's a little bit lower than solid state, but for simplicity, we consider it as a solid state, and it reduces to the surrounding density. So we our model we specified external plasma density is 10 in 18 per cubic centimeter, and this was a parameter of a problem. It results from observation or from our previous estimation, previous modeling results when we use this plasma to product explosive events, and it was like a threshold density because we need large enough density to transfer a current from emission. So it
oops. It's probably the connection. The connection is lost. So unfortunately, Mikhail is not able to answer the question from Igor Imanov, which is have you compared your rating on the heating of the liquid jet drop neck with the results of direct modeling of this process? So I believe that Mikhail can answer this question in the forum. Okay, thanks again, and we are switching to the next presentation. This presentation is made by Pavel Ruskich from the Institute of Electrophysics, Russia, and the title of the talk, durability of inductor material with inhomogeneous resistance under high pulse magnetic field generation. Please, Pavel. Pavel will give his presentation in Russian, and the translation will follow. Okay.
Good afternoon, colleagues. I'd like to present you results of my work in Russian. Let's get started. Моя работа посвящена теоретическому исследованию стойкости проводника с неоднородным сопротивлением в сильных импульсных магнитных полях.
Pavel, could you please repeat your
Repeat? Yeah.
later is now here.
Моя работа посвящена теоретическому исследованию стойкости проводника с неоднородным сопротивлением в сильных импульсных магнитных полях. Одним из перспективных направлений...
Please give sufficient time for the translation.
Okay. Can you hear me okay?
Yes.
All right. So my work is devoted to theoretical investigation of the durability of a conductor in strong magnetic fields.
Одним из перспективных направлений электрофизики является магнитно-импульсная обработка материалов.
So one of the most promising direction of electrophysics is treatment is magnetic pulse processing of materials.
На слайде представлена магнитно-импульсная сварка, самый напряженный из способов магнитно-импульсной обработки.
So in the slide you can see magnetic pulse welding. It's the most difficult type of welding. It's the most difficult type of processing.
Основной инструмент обработки – это индуктор. На слайде представлены различные конструкции индукторов.
So the main instrument for processing is an inductor. You can see different designs, different constructions of inductors.
Основная проблема технологии возникает при работе в напряженных режимах.
So we usually have problems when we work in intense regimes, when we work in intense modes.
К примеру, пытаясь получить поле амплитуды 50 Тесла и выше.
For example, when we're trying to get a magnetic field with an amplitude of 50 Tesla and higher.
Во время импульса тока поверхность нагревается, образуются трещины, что в итоге приводит к полному разрыву индуктора.
So during the current pulse, the surface gets really hot, and it leads to its damaging, and the inductor actually gets destroyed.
Так как разрушение для нас нежелательно, то мы стали искать в литературе, каким образом можно увеличить ресурс индуктора.
Of course, we want to avoid this problem, so we started looking in the literature. We started looking at possible ways how we can increase the operational life of the inductor.
Наше внимание привлекла работа Шнейерсона, в которой анализ тепловыделения для среды с сопротивлением, спадающим по экспоненциальному закону, показывает, что плотность объемной энергии уменьшается в 5 раз при уменьшении сопротивления в 5 раз.
Okay, and we found this interesting paper by Shenenson, and in this picture you can see the dependence of resistance on the distance, and you can see that resistance decreases as by a factor of 5 as the distance increase.
Таким образом, мы посвятили нашу работу изучением этого подхода для различных профилей сопротивления.
So, in our future work, our current work is devoted to the study of this approach, and in particular, we're studying different profiles of resistance.
Таким образом, целью моей работы стало исследование стойкости материала индуктора во время генерации сильного магнитного поля, и нужно было решить следующие задачи: написать программу для моделирования и создать модель, и проанализировать результаты, и выбрать наилучший способ модификации.
So the aim of my work was to study a durability of the inductor material with inhomogeneous resistance under high pulse magnetic field. And I had to solve the following task. First, I need to write a computer program for simulation of the processes, and then I need to analyze the results and find the best parameters for modification.
Одномерная задача решалась в плоской геометрии.
One-dimensional model was solved in flat geometry.
Векторы плотности тока и напряженность имели только Y-компоненту, а напряженность поля только компоненту Z.
Okay, vectors of current density and field intensity had only Y component, and so what was the other one?
Напряженность поля только компоненту Z.
And so the field strength had only Z component.
Использовались нулевые начальные условия, а граничные условия для уравнения диффузии магнитного поля на границе x равно нулю задавалось в виде затухающей синусоиды.
Okay, so the boundary conditions were set as given in the equation. It was a damping sign form.
Параметр BM определяет амплитуду кривой и далее будет использоваться как параметр, определяющий амплитуду поля.
So the B parameter defines the amplitude of the curve, and further we will use this parameter to define the amplitude of the field.
Во время диффузии магнитного поля условия для температуры были адиабатическими, а после диффузии на границе x равно нулю, x равно L, принималось нулевое граничное условие до полного остывания материала.
Okay, that was too long. Let's translate bit by bit. Can you please repeat the bit about magnetic diffusion?
В процессе магнитной диффузии граничные условия для температуры были адиабатическими.
Okay, during the magnetic diffusion, the boundary conditions for temperature were adiabatic.
После магнитной диффузии на стадии остывания граничные условия на дальней границе было равно нулю.
So after magnetic diffusion, when cooling took place, boundary conditions were equal to zero.
На слайде представлены уравнения, которые нужно было решить. Сверху это уравнение магнитной диффузии, снизу уравнение теплопроводности.
Okay, in this slide you can see two equations that we had to solve. The first equation at the top of the page is the equation for magnetic diffusion, and the second equation is heat conduction equation.
Электрическое сопротивление задавалось как функция от температуры и пространства.
Okay, electric resistance was set as a function on temperature and space.
Начальная пространственная зависимость сопротивления задавалась при помощи трехпараметрической функции.
Initial spatial dependence of resistance were set as y-x function, as you can see.
На первом рисунке мы видим влияние первого параметра, он определяет амплитуду модификации.
Okay, in this picture, you can see the influence of the first parameter. The first parameter defines the amplitude of modification.
Второй параметр определяет глубину модификации.
The second parameter defines the depth of modification.
Третий параметр определяет форму модификации.
The third parameter defines the shape of modification.
Воздействие магнитного поля записывалось при помощи этого уравнения.
The influence of magnetic field was described as this equation.
На стадии упругого деформирования напряжение материала описывались при помощи закона Гука.
So at the stage of elastic deformation, we used Hooke's law to describe the behavior of material.
На стадии пластической деформации мы использовали уравнение, исходящее из критерия Мезиса.
During the stage of inelastic deformation, we used this von Mises criterion.
Перед вами результаты моделирования для профиля из стали 30 ФГСА со следующими параметрами.
Okay, in this slide you can see the results of our simulation. The item for this simulation was made of stainless steel. The model of stainless steel you can see here.
Первый рисунок показывает распределение магнитного поля от пространства в период максимума поля на границе.
The first picture shows the distribution of magnetic field for the case when the magnetic field was maximum at the boundary.
Второй рисунок показывает нам распределение температуры на конец процесса.
So the second picture shows the temperature distribution towards the end of the process.
И третий рисунок показывает нам распределение пластических деформаций на конец процесса.
And the third picture shows the distribution of inelastic deformation towards the end of the process.
Как мы видим, более глубокая диффузия поля приводит к распределению нагрева на больший объем.
As we can see, that the deeper distribution of magnetic field leads to what? Can you repeat that, please?
К распределению температуры на большее пространство, на большее расстояние.
Leads to that fact that temperature is being distributed to a deeper region.
Что приводит к меньшим пластическим деформациям.
And that fact leads us to fewer plastic deformation. So the plastic deformation decrease.
Перейдем к анализу стойкости.
Okay, let's analyze the durability of materials.
Было обнаружено, что максимальное значение поля, при котором пластическая деформация возникает, растет с увеличением амплитуды модификации.
Okay, we found out that the maximum value of magnetic field at which plastic deformation occurs rises as
Амплитуды модификации.
as amplitude of modification rises.
При увеличении сопротивления на поверхности в 2,5 раза максимальное магнитное поле удалось увеличить с 47 до 56 Тесла.
Okay, when we increase resistance on the surface by 2 times, we managed to increase the maximum magnetic field so how the magnetic field was increased?
Магнитное поле от глубины модификации.
So the magnetic field was increased from modification depths.
Что касается зависимости от пространства, существует ярко выраженный максимум, который смещается вглубь материала для более высокорезистивных покрытий.
Okay, if we look at the dependence on the space, we can see that there is a maximum which moves to the depth of materials for materials with higher resistivity.
Что касается формы профиля модификации, то наилучшая форма оказалась близкой к линейной.
As for the shape and profile of modification, the best option was lineal.
Таким образом была решена задача диффузии магнитного поля в проводящий слой.
So by doing that, we have solved the problem of diffusion of magnetic field into a conducting layer.
В результате было обнаружено, что высокорезистивный поверхностный слой может заметно повысить стойкость индуктора в магнитном поле.
And we found out that so the magnetic
Высокорезистивный поверхностный слой
high resistance surface layer
может заметно повысить стойкость индуктора.
Can significantly increase the durability of inductor
в магнитном поле.
In magnetic field.
Thanks for your attention.
I hope you with the questions as well.
Thank you very much, Pavel, for your presentation. And I see a question from Ivan Yegorov. Do you plan to test the idea by experiment? What difficulties do you see in reproducing your model in reality?
Now our colleagues works on experimental realization of our research. What about difficulties? As you can see, as you could see, the magnetic field is it's about 40 Tesla, and it's very high field, and it's not easy to create the installation for experiment.
Thank you. There are probably no more questions. I have a question.
Okay.
Pavel, you solved a one-dimensional model, yes?
Mm-hmm.
Right?
Yeah.
Do you believe the one-dimensional approach is sufficient to describe the most experimental situations? Or you expect some principal effects from the curvature, the dimensional effects, which will make it necessary to perform 2D or 3D simulations?
Yes, it will be our next steps. The results which you see, it's our first steps.
Mm-hmm. Thank you very much again.
Thank you.
The next two talks will be made by Dr. Almay Sayfutdinov from Kazan National Research Technical University, named after Tupolev, Kazan, Russia. And the first talk title is Numerical Study of the Kinetics and Gas Heating Effects and the Formation and Evolution of a Microwave Streamer in Air. Please, Dr. Sayfutdinov, this is your floor. Okay. Please press the green button.
I'm sorry, we have some technical problems with the other translator. It looks like she cannot go on air, so it's going to be me again. If you need help, I'm just going to translate again.
I believe the three talks, two talks by Dr. Sayfutdinov and the talk by Kamila Ashurova will be made in English, right?
Okay.
Ждем. Okay, Almas, are you here? Some problems, still some problems. Support. Almas, you can go to the support system. Кто там в саппорте сидит? Ага. Almas, which kind of problem do you have? Ага. Он же выходил? Okay, the speaker has some problems, and I propose to wait a while. Mm-hmm. Mm-hmm. Okay, well, the problems are still here. I propose to go to the presentation by Kamila Ashurova. Yes, Kamila, we see your presentation. Oh.
Hello.
Hello. Almas?
Oh, me, Almas Seyfudinov, yes.
Yeah.
Sorry, problems with camera and microphone.
Okay, now we see you and we hear you. So we can return to Almas Seyfudinov's presentations. Kamila.
Okay, thank you.
I apologize. So we are going to our basic scenario.
Okay, this presentation about numerical study of the kinetic and gas heating effects on the formation and evolution of microwave plasmoids in molecular gases. My name is Seyfudinov Almas. I am from Kazan National Research Technical University. Advances in microwave electronics created possibilities to initiate various types of microwave discharge in a wide range of external conditions. According to the initiation method, microwave discharges can be classified as follows. Microwave discharge on surface wave, for example, in surfatrons, discharges based on microwave resonators, on microwave transmission lines, electrode and electrodeless discharges, free, localized, and all focused microwave discharges. All these discharge types are widely used in various fields of modern science and technology. Next slide. Yes. Modern science and technology, for example, in particular, they are applied in plasma chemical synthesis, in sterilization and plasma biomedicine, in treating environmental problems, in analytical chemistry, in plasma photonics crystals and metamaterials. Fundamental studies of microwave breakdown at intermediate and high pressure, in particular atmospheric, dynamics and shape of plasma structure in focused and free localized microwave discharge inspired increasing interest in their application in aerospace technologies. For example, a series of experimental study demonstrate a high capability of microwave discharges for the energy deposition to supersonic and hypersonic gas flows aimed at flow control and drag reduction. Special focusing devices based on a spherical mirror as well as mirrors in the form of cylindrical paraboloid. Next slide, please.
Oh, you can change the slides by using arrows right and left arrow, you see? In the lower part of the screen, there are two small arrows. Okay, let me change the slides. Slide number 3.
Yes, number 3, cylindrical paraboloid were developed and impact of microwave discharge created in such system on gas heating in supersonic flows was shown in these works. Analysis of accumulated experimental results showed that focused microwave discharge represent a complex nonlinear phenomenon, including unsteady breakdown, propagation of ionization fronts, interacting with microwave radiation, excitation of molecules accompanied by natural gas density variation. The diversity, high rate, and coupling of the physical processes in a microwave discharge make it extremely challenging to measure experimentally the plasma parameters of such discharges. Only integral or estimates values of main characteristics can be obtained, and often by indirect methods. Thus, in these works, in third works, in experimental measurements carried out in the of the front surface of cylinder in a supersonic flow was studied under condition of energy input 1.5 millijoule by using a focused microwave discharge. It was concluded that for perfect gas model and instantaneous energy deposition in microwave discharge, the gas temperature is heated domain increase 500 kelvins. Along with experimental techniques for studying discharge and their application, numerical methods are rapidly developing, allow not only to explain the observed plasma phenomena, but also to predict the characteristics and optimal operating modes of designed device. During the last decided experimental results obtained early for free localized microwave discharges gave a boost to a series of theoretical studies. In this work, microwave breakdown was simulated numerically under various conditions in order to reproduce formation of plasma streamers and filaments observed in experiments. Simulations were performed using not only one-dimension approximation, but also two-dimension, three-dimension formulation. For the discharge plasma description, a simplified approach was used based on the equation of ambipolar diffusion with a modified diffusion coefficients. It was assumed that the main source of electrons in the discharge is provided by electron impact ionization. The loss of electrons was specified by attachment and recombination. Gas molecules were supposed non-excited and in early studies not heated. Later, in another work of Professor Boeuf, gas heating was taken into account under assumption that the fraction of energy spent in an elastic process is transferred to the translation energy. The validity of this assumption was justified in another work. As a result, filamentation and development of a network of microwave discharge streamers in air at atmospheric pressure was reproduced numerically. Moreover, gas heating and its influence on the formation of a single microwave discharge streamer was described in several works of in Russian scientists, for example, Khodatayev, Yasakov, and others. For such models, it was possible to interpret experimental measurements mainly for the cases when the low temperature plasma evolution is specified by purely electrodynamic effects. In our works, our purpose of our works is in the framework of numerical experiments to study gas heating dynamic and spatiotemporal dynamic of the formation of active phase and passive path of a focused pulsed microwave discharge in molecular gases according to conditions of experiments conducting in gas dynamics laboratory in St. Petersburg State University. And this task we should to solve to follow this purpose. Next slide. The description of the description of microwave discharge in molecular gases is based on extended fluid model. Under considered conditions, the mean free path of charged particles is considerably shorter than the characteristics length of the problem, and therefore the continuum approach can be used for the flow simulation. In general case, for the microwave discharges description, it's necessary to solve the Maxwell equations. However, in the case of plane wave propagation, Maxwell equations are reduced only one complex equation for the wave's electric field. It's Helmholtz type equation for the complex electric. The solve this equation with the boundary conditions. Allows one to calculate the power transferred from the electromagnetic field to electrons. To determine the spatio-temporal characteristics of the focused microwave discharge, we generalized the extended fluid model. It consists several equations. First equation, the density continuity equation of particle, neutral particle, electrons, charged particles, and excited particles, and also fluxes. Fluxes in this equation is include diffusion and Drave terms. Next equation, the equation of mean energy, electron energy, and Poisson equation. Next block of theoretical model is fluid mechanics and thermodynamics. It consists the heat transfer equation, Navier-Stokes equation, and equation of vibrational energy of nitrogen. And also in this slide we can see K channels of natural gas heating as the energy transfer in elastic collisions of electrons and neutral particles, energy transfer due to recombination, quenching of electronically excited states, and vibrational relaxation. In our numerical experiments, we make for two gases. In first series numerical experiments, we used pure nitrogen, and here we can see excited states in plasma, which we include, and also here all reactions in pure nitrogen. And also we used two set of fast gas heating channels. First series of experiments, we used first this table, and in second we used all these reactions. On this slide we can see computational domain for the two-dimensional case, and boundary condition and initial conditions. On this slide, we can see results. Here we can see spatial distribution of electron density at different times. And in next slide, the electric field. It can be seen that the first plasmoid is already formed at main focus of the system by the time of 0.4 microsecond, the density of electrons reach value approximately 8.5 on 10 in 18 per meter in cube, which is almost comparable due to critical value of electrons in plasma for a given frequency determined by the formula, and critical equal proportional frequency of plasma plus elastic collisions. At the moment 0.45 microseconds, the electron density reaches the value 5 on 10 in 19th per meter in cubic, and at the moment 0.65 microseconds, the maximum value is 10 on 10 in 19th for the entire duration of microwave pulse. As a result of the formation of the first plasmoid, as can be seen from these figures, there is a spatial redistribution of the electric field. At the instant 0.65 microseconds, the second lower plasmoid begins form, and the maximum of the electric field strength located closer to the microwave radiation source at the distance approximately lambda or divided on 4. Further, there is an increase in the electron density in the second plasmoid and slight decrease in the first. The spatial distribution of the electric field value changes again. By the time 0.7, the electron density in both plasmoids excited the critical value, and in the upper and lower plasmoids respectively. From this moment, the formation of two more plasmoids is observed near the reflecting surface at the maximum of the electric field strength. And by the time 1 microsecond, the electron density in them reach maximum values. From this moment, the structure of the main and lower plasmoid changes to symmetrical branches are formed each. Thus, by the time instant of 3 microseconds, 4 plasmoids are observed in the computational domain. The first at the main focus of the system, the second, the lower one located near the microwave radiation source, which is a structure of 3 grouped plasma formations, as well as 2 upper plasmoids symmetrically located near the surface of parabolic mirror. Next slides. This slide shows the dynamic of spatial distribution of gas temperature. It can be seen that after the formation of the first and second plasmoids, the gradual heating is observed. In this case, the maximum temperature in the active phase of the discharge is observed by the time instant 3 microseconds in the first plasmoid and the main focus of the system, and is 395 kelvins. In the second plasmoid, the gas temperature reaches 338 kelvins. In the 2 upper plasmoids, the gas temperature reaches 330 kelvins. Next slide shows spatial distribution of the vibrational temperature of nitrogen at different times. As we see, at the time of 3 microseconds, vibration temperature reach 500 kelvins. In the case using the second set of gas heating mechanism, including the process presented in these two tables, the picture remains qualitatively. 4 plasmoids are formed. However, the quantitative characteristics, in particular the vibration temperature and gas temperature, became higher. Since in practice, in particular in plasmoids applications, the behavior of plasma parameters in the afterglow phase is of interest. lets us trace the dynamics of change in main plasma parameters in the main plasmoids over the entire time scale from 0 to 1 millisecond. In the active phase from 0 to 3 microseconds, and in the afterglow here. Here we can see electron density, the translational gas temperature, and the vibrational gas temperature for two sets fast gas heating reactions. A qualitatively similar form is observed in the behavior of the electron density as well as vibrational and translational temperatures, but there are differences in the quantitative values. So after reaching the maximum of the electron concentration density, its weak decrease is observed, and the approach to close the equilibrium value. Then after tuning of the microwave electromagnetic field, the electron density begins to drop sharply in the interval from 3 microsecond to 10 microsecond. In the interval time from 10 microsecond to 1 millisecond, the electron density decreased by another 2 order of magnitude for the first set gas heating mechanism, and by the 3 order of magnitude the second set of gas heating mechanism. After the end of active phase of pulsed discharge, the vibrational temperature of nitrogen continues to increase in the time interval from 3 microsecond to 10 microsecond to 850 kelvins for the first set of gas heating mechanism, and up to 880 kelvins for the second. And then it begins to decrease in the time interval from 10 microsecond to 1 millisecond. Its values drop to approximately 400 kelvins respectively. The dynamics of the gas transition temperature in active phase has a stepwise form. A sharp increase in observed in the time interval. In this time interval, during the formation of the first plasmoids, from to 358 kelvins and 396 kelvins respectively for 2 sets of gas heating mechanisms. Then by the end of the microwave pulse, the temperature increased to 390 kelvins and 460 kelvins respectively for the first and second sets of gas heating mechanisms. In the afterglow phase, the gas temperature continued to rise up to 10 microsecond and is 420 kelvins for the first set of gas heating mechanism up, and 70 microsecond and is 500 kelvins for the second set. Further, a slight decrease in temperature is observed at the moment time of 270 microsecond. The vibrational and gas temperature are equalized for the both set of gas heating mechanisms. The higher reach of the main gas heating channels for the 2 considered sets as different times are shown on these figures. In the case of the first set, the main gas heating channels during the first fraction of microsecond of the active phase, and the release of the energy in self-quenching reaction of excited nitrogen particles. The release of energy in the dissociation reaction then is the subsequent part of active phase. The domain mechanisms is a reaction self-exciting which dominate up 6 microsecond. And next we can see that vibrational translational mechanism is dominate. And here for second step of gas heating mechanism, analogical situation, we can see here on this slide we can see time dependence of excited particles and different types of ions in plasmoid located at the main maximum of focusing system. And here we can see spatial distribution of the electron density, gas temperature, and vibrational temperature at different times in the afterglow plasma of pulsed microwave discharge in nitrogen. And here we can see spatial distribution of the electron density at a fixed value of electric field strength in the input of the waveguide and pressure 60 and 70 torrs. We can see here formate 2 plasmoids, and when pressure is equal 70 torrs, we can see only 1 plasmoid formate in numerical region. In next step, we make experiments in another geometry. We another geometry. It's interest to study the details of the formation and dynamics of single microwave plasmoids and scratching along the electric field. In connection with the above equation of microwave discharge were solved numerically for this domain. In order to form one plasmoid in computational domain, two identical linearly polarized wave from both sides of two-dimensional rectangular modeling domain were considered opposite direction top and bottom to form standing wave. The size, this is size of simulation area. At the lateral boundaries, the computational domain, the condition of the passage of microwave were set in another slide. In this formulation, only one anti-node is formed in the computation domain in a standing wave. Despite the fact this formulation of the problem is to some extent a model, it allows one to study the dynamic properties of single microwave plasmoid in stretching along the electric compound of the microwave electric field. Here we can see some results, analogical initial conditions. Here we can see contours of electron density, and here we can see electric field. Electric field, it sees that as along the plasma density is low and does not disturb the electromagnetic field. At time 0.3 microsecond, the maximum plasma density is this value, and the applied microwave electromagnetic field begins to be significantly modified by the plasma. Moreover, and the effect observed similar to the dielectric sphere, it's a constant external electric field. Polarization effect tend to enhance the electric field at the poles of the plasmoid in the direction of the field. Direction on the field. Okay, by the time instant 1 microsecond, the plasmoid length is equal approximately 5.5 centimeters. In this case, the electron density maxima are shifted to the heading from the plasmoid growth, where the electric field strength has maxima and reached 3.5 kilovolts on centimeters, which is more clearly see in this figure. In this case, in the center of the plasmoid, the field falls below the critical value in connection with which a decrease in the electron density is observed. On this slide, we can see spatial distribution, the gas temperature and the vibrational temperature of nitrogen. And we can see that the gas temperature approximately also, sorry, I can see 380 kelvins. And here we can see the profile density and electric field along the streamer axis. Also, we make these experiments, analogical experiments for air. Here we can see kinetic scheme for the reaction, plasma chemical reaction in the air. And on these slides, we can see some results in analogical situation. We can see also makes several plasmoids in numerical domain. And on these slides, we can see spatial distribution of gas temperature and vibrational temperature in nitrogen at different times. And on this slide, we can see conclusions. Thus, in this work, extended fluid model of a focused microwave discharge has been formulated, and numerical experiments have been carried out on the formation of the active phase and in the passive phase of pulsed microwave discharge in molecular gases in a focusal system in a two-dimensional geometry, and has demonstrated an effective way of supplying heat to supersonic gas flows. As a result of numerical experiments, it was demonstrated that in proposed focusing system, depending on the gas pressure and microwave power, from 1 to 4 plasmoids can be formed, two of which are formed along the Horn axis, and two symmetrically located related to the Horn axis. The dynamic of the main parameters of plasma of this discharge is obtained. The dynamic of heating of natural gas, the vibrational temperature of nitrogen is obtained. It has been demonstrated that the gas heating is also observed over a long time interval in the afterglow phase. Numerical calculations have been performed to study the stretching of a single plasmoid along the electric field. And preliminary computational experiments on the formation of microwave discharge in air have been carried out. Thank you for the... Here we can see references, and thank you for your attention.
Thank you, Dr. Seyfutdinov. We are going to questions. For a while, I don't see any questions. I have a question to you. What about the software, the code you used? Is this your own code, or you use some commercial codes?
Yes, thank you for the questions. For the first domain, this domain, we COMSOL multiphysics, and for this we used our code for this geometry.
I see. As I understand,
we have some difficult. In first, we make numerical experiments in air, and COMSOL cannot solve many reactions in air when fraction of different natural particles is equal. For example, nitrogen, oxygen, and its excited particles. That's why we make some self-code.
I see. Using COMSOL, you did 3D simulations. Yes, right?
Yes, yes.
And using your own code, you did 3D or 2D simulations?
Only two-dimensional.
Only two dimensions. Thank you. So I believe there are no more questions for a while. So you can switch to your another talk. I advise you to, since we have some small shortage of time, I advise you to give the presentation in maybe with less details. And if you need, we can go to the forum for a detailed discussion. So the next talk by Dr. Seyfutdinov is titled Non-Equilibrium Modeling of DC Nitrogen Microplasmas from Glow to Arc Discharge. Please. So you can start.
I don't see presentation.
I do. I see your presentation. The first slide is on. Your slides are here.
Oh, yes.
Okay.
Okay, this presentation will be shorter because I have not a lot of time. On this slide, we can see some application of atmospheric pressure glow discharges. And as we know, gas discharge plasmas at atmospheric pressure have become a source of increasing interest in recent years as object for the study of fundamental plasma phenomena, and from the point of view of their practical application. Non-equilibrium plasmas at atmospheric pressure are produced in a range of scale submillimetric, at least in one direction, in constant or variable electric field and various frequency ranges. At the same time, two main types of the discharge can be implemented in the DC plasma generators: glow discharges and the electric arc discharges. Glow micro discharges are widely used in radiation source, in plasma synthesis, in device of surface treatment, and other. Micro arc discharge are also becoming increasingly significant, for example, in additive manufacturing, micro welding, and nanostructure synthesis. It is worth noting, however, that the small size of micro discharge at atmospheric pressure makes their experimental diagnostics an extremely difficult task. Discharge properties often have to be interfered from their integral electrical or spectral characteristics. At the same time, it's useful from the both practical and theoretical points of view to have knowledge the spatial distribution of the main parameters of the discharge plasmas. It is obvious that missing experimental data can be filled in applying methods of numerical simulation of the discharge processes. It should be noted that the modeling of both types of DC discharges, namely glow and electric arc discharges, has developed through parallel and independent pathways. The description of glow discharge relied on fluid, kinetic, and hybrid models with varying degrees of detail of the process occurring in the discharge depending on the problem statement. The accuracy of mathematical models is largely determined by the knowledge of the initial data. For the electric arc discharges, used magneto-hydrodynamic equations, and these both approaches are valid and justified. And in our previous work, we make a simulation for the transition from the glow to arc discharge in argon. Also, these numerical experiments makes Professor Baeva. In Professor Baeva make experiments only one-dimensional geometry, and we make for two-dimensional geometry for argon, for inert gases. And interest to make experiments for the molecular gases, for example, for nitrogen. On this slide, we can see theoretical model. Extended fluid model is formulated. It consists the density continuity equation, the equation of the mean electron energy, Poisson equation, and heat transfer equation in the gas discharge plasma. Also, we use the balance equation for the energy of heavy plasma particles and balance equation of the vibrational energy of nitrogen. Here we can see a diagram describing the main mechanisms that determine the gas heating in DC microdischarge at atmospheric pressure. Here we can see geometry and computational domain. and computational domain. Let's us consider the boundary condition. For the our system equation, a large number of processes occur at the boundary between the cathode and the gas discharge plasmas. In the first place, those processes maintain the glow discharge. One of them is the secondary electron emission from the cathode, which occurs as a result of the bombardment of the cathode with ions that have accumulated energy in the cathode layer. On the other hand, the rise of the cathode temperature to critical value as a consequence of the heat flow from the discharge gap, namely from the cathode layer, leads to thermionic emission from its surface. The current density of thermionic emission is given by the Richardson-Dashman formula. In connection with the foregoing the boundary condition for the electron flux, electron energy flux, fluxes of the ions and excited and neutral particles of the plasma on the metal electrode, taking in this form. Also, as a boundary condition of the Poisson equation, we assume that the cathode was grounded, and on the anode we input some voltage, which founded from this equation. We determined the boundary condition on the temperature of heavy particles at the cathode and the anode from the solution of the thermal balance equation of the electrodes on the cathode and the anode. The boundary condition for this equation on the cathode surface on the side of the plasma was writing this form. The first term on the right hand side describes the density of ion energy to the cathode. It includes the density of the kinetic energy of the ions, mainly in cathode layer, and the density of potential energy which, when transferred to the cathode, caused by neutralization of the ions. The second term of the right hand side describes the density of the thermal flow from the heated gas near the cathode. The third term on this corresponds to energy flow from the cathode surface determined by the energy exponentially on both secondary and thermionic emissions. It is worth noting that a part of electrons that leave the cathode during the emission caused by elastic collisions with neutral gas particles can change the direction of their movement for the opposite. At the same time, if their energy is sufficient to reach the surface of the cathode, they will increase the heating. The follow density of energy of backward electrons in this case given by this formula. The boundary condition of this equation at the anode touching the plasma region was writing by this. It includes also gas heating, electron bombardment, and ion bombardment. This is a set of plasma chemical reactions in nitrogen. It's analogical like in first presentation where microwave discharge we studied. And here we can see some results. On this slide, we can see dependencies of the voltage, black, and surface temperature of the cathode and the anode on the current density for the discharge gaps of 0.4 millimeters. And here we can see distribution of the components of electron current density at the cathode, thermionic emission, secondary electron emission, and backward electrons. And this slide, so we can see dependencies of this mechanism of heating the surface of the cathode and the anode on the discharge current density. All these results can to describe a transition from the glow to arc discharge. we can see its normal glow discharge, its transition region from Townsend to glow discharge, its anomalous glow discharge, here transition from anomalous to glow discharge, and here, or to arc discharge, and here is arc discharge. Next, we can see distribution of the electron density, the sum of densities, all types of ions, and density of various types of ions, the strength, electric field and potential, translational and vibrational and electron energy, and various mechanisms of gas heating for the glow discharge and for the arc discharge. We can see in the arc discharge cathode fall region is very small, and in all regions we can see quasi-neutral plasma. Also, it's interesting to investigation how influence boundary conditions in opposite side of electrodes. First results we find when our temperature is constant, room temperature. And in second case, we used these boundary conditions. And for the arc region of the discharge, we can see that in cathode region, negative space charge. Also in vacuum diodes situation realized with minimum potential. And on this side, we can see dynamics of the formation of potential drop, heating of the electrode surface for the two cases of boundary condition in outer walls of the electrodes. This line for the temperature constant, and this line is temperature found by these formulas. In the cathode region, we can see that potential drop in cathode region for arc discharge for this situation is smaller than in this situation. And on this slide, some conclusions. In this work, we suggest a unified and self-consistent model based on extended fluid model of plasma formulated in terms of the description of the discharge gap and the electrodes. The model makes it possible to describe various types of DC discharge modes in molecular gases, for example, in nitrogen at atmospheric pressure. Under the framework of the model, we conducted a series of numerical experiments for this interval of current density. We obtain a classical dependence between the voltage across the discharge gap and the current density. For each value of the discharge current density, we find all main parameters of the discharge: number, densities, charge and excited particles, electric field distribution, potential distribution, temperature of electrons, heavy particles, and vibrational temperature. We determine the main mechanisms of gas heating. Thus, the main mechanism of gas heating is quasi-neutral region of the discharge, is vibrational, translational, relaxation along with the energy release in reaction of dissociation and quenching of excited nitrogen molecules. We obtain distribution of components of the electron current density at the cathode under the action of thermionic emission and secondary electron emission, as well as the current density of backward electrons depending on the discharge current density. And also we describe the scenario of development of free arc mode, arc discharge, free cathode region. Its usual characteristic features, namely negative volume charge. The cathode layer presents of a minimum of potential and sufficiently low density of charged particles in arc core. Here are some reference of our work. Thank you for your attention.
Thank you, Almaz. for the very interesting presentation. Now we are going to questions. No questions for a while. I have the same question about the code you used for this your research. Was it console or your own code?
For this research, we used and both console and other our codes. C++.
Yeah, I see.
Yes.
Thank you very much. And the talk finalizing our today's program will be held by Kamila Ashurova from Tomsk State University for Control Systems and Radio Electronics, Russia. And the name of the talk is Numerical Simulation of the Effect of an Electron Beam on the Surface of Materials. So I give the word to Kamila Ashurova.
Hello, everyone. Can you hear me?
Yes, we can hear you.
So, good afternoon, dear colleagues. It's nice to see you all, and I'm very glad to present this work on the IFRE 2020. So today I'm going to be talking about the numerical simulation of the effect of an electron beam on the surface of materials. Modification of materials surface, one of the most actual topic, as it allows to improve a lot of functional characteristics for use in the different fields, such as medicine, biology, and industry. Namely, irradiation of material surface by electron beam allows to increase such properties as wear resistance, fatigue life, corrosion resistance, and reduce the structure to the nanoscale range, which leads to the reduce of the roughness. In this work is used electron beam with a grid plasma cathode based on an arc plasma discharge. So advantages of using such plasma cathodes are presented on a slide. It's independence of parameters from each other, wide range of beam parameters adjustment, and high energy efficiency. The name of this electron source is SOLO. Main parameters are presented on the slide. Also, in the figure 1, you may see the general view of the source and detailed diagram of the source. So the initiating discharge is ignited between hollow electrode and cathode. The main arc discharge is burning between cathode and hollow anode. The current voltage is applied between the emission electrode and extracting electrode. Electrons from the beam are transported to the collector through the drift tube in the magnetic field of 2 magnetic coils. So the main material that was modified in this experiment is steel. One of the oscillogram from this experiment is presented on the figure 2. You may see on this oscillogram 4 curves. The first one is discharge current, a current in the accelerating gap, the accelerating voltage, and sample surface temperature. So the main purpose of the study was to conduct a numerical simulation of thermal processes happening in the surface layer of different materials. So in order to conduct it, we have to solve a heat equation, which takes into account 3 main points. The first one is the phase transition. The second one is the temperature dependence of the thermophysical coefficients, and also the boundary conditions at the sample boundary presented on the slide. Also, on the slide, you may see a function that characterizes an external heating source, which is determined in accordance with the experimental power. In the framework of my experiment was also shown a solution of heat equation for aluminum and titanium. So on the figure 3, you may see the dependence of power density for both materials, and so they have the similar function, and using those function we get a solution of heat equation, which is presented on the figure 4. So you may see the dependence of surface temperature for aluminum and titanium, and you may see that the both curves actually have the same trend of changes. So that is why we may say that by controlling the power density, we may actually control the temperature of the surface of different materials. So it doesn't matter what kind of material, and we can control it. Back to our main experiment with steel. You can see on the slide 6 the result of numerical simulation, namely figure 5b shows the dependence of target surface temperature. So the red curve is the experimental one, and the blue is calculated one. And you may see that there is a satisfactory agreement between the experimental data and calculated data. The peak shows the end of the pulse. There is a difference between two curves in the peak, which happening because of sputtering of target during the irradiation by electron beam. Then you may see the plateau, which relates to crystallization processes happening in material. And then you may see the difference at the end between two curves. It is happening because of changes of thermophysical coefficients from the temperature in the surface layer. Because we see satisfactory agreement before, we also wanted to show different ways of analyzing those thermophysical processes happening in the surface layer. So for example, in the figure C, you may see the temporal distribution of temperature at different depths. So on the figure 7, there are isotherms in the space-time plane. So from that graph, you may find out information about for example, with the red line, we may say that the surface of target was heated for 1800 kelvins for 10 micrometers. And then on the figure 8, there is a temperature distribution over depth at different time moments. So as I mentioned before, by controlling the power density, we may control the temperature of the surface of our target. But there are actually several ways of putting energy into target. So for example, in the figure 9, you may see the oscillogram 9A. There is a current in discharge current. By discharge current, we control the current in the accelerating gap, and so in that way we control the form of the power during the pulse. So you may see that the form of the power almost repeat the form of the current in the accelerating gap. In the same situation in the figure 9, B and D. Also, on the slide 9, you may see two different ways of putting the energy. The 10C shows the increasing trend, and the 10D shows the decreasing trend of putting this energy. So that is why by controlling the amount of power, we also can control the amount of temperature of the surface and the way how it changes. So in the conclusion, I want to say that in this work, experimentally and theoretically was shown the possibility of controlling the surface temperature of sample, and also numerical simulations show a satisfactory agreement between the calculated values and experimental data. And also in this work were shown different ways of changing the current during the electron beam pulse and changing the form of the power. So thanks for your attention.
Thank you, Camila. About the questions, I see no questions in the forum. I have a question to you. Is it your own coding?
There are actually, it was, the numerical simulation was conducted in a MATLAB. So there was two ways. In the MATLAB, можно я на русском отвечу?
You speak in English very well, so please try to answer in English.
Okay. In the MATLAB, there was a program which give us a numerical simulation, and also there was a code. Yes, the code was written by my computer, so that is why we get result.
Thank you. I see a question from, I believe, Ivan Yegorov. What are the ways to increase the accuracy of the modeling?
In this work, we didn't counted the sputtering of the target, so we didn't calculate at this moment that the heat actually goes away. So I guess that in the future we will calculate that the little amount of the target is actually sputtering, and I guess it will get a more accurate result.
Thank you. So I see one more sentence from Ivan Yegorov, but what is the question? I don't understand. Peak modeling? Oh, so it's probably not a question. Okay. So our today's program is finished. We are concluding our session. So again, very much to all the participants, to the speakers, and to those who were listening to these talks. Again, I invite everybody to use the forum for detailed discussions of the presentations and for any other discussions. Again, you have the opportunity to organize your own round tables. So I'm looking forward to see you in the forthcoming days of the Congress. So thank you very much again. Bye-bye.